Okay, now we will start with example 27.5. This example is related to drift velocity, uh, an article which we have used the model Jude's model. So its A part says that using the data and results from example 27.1, which we have already done, and the classical model of electron conduction, estimate the average time interval between collisions of electrons in household copper wire. So what we require over here is the data that is given. This is taken from example 27.1. uh, the resistivity of copper, which is 1.7 into 10 to the power minus 8 ohms meter. Then we have the number of charge carriers, that again from example 27.1, which is 8.49 into 10 raised to the power 28 electrons per meter cube. Mass of electron is 9.11 into 10 to the power minus 31 kilograms, and charge on electron is 1.6 into 10 to the power minus 19 coulombs. What we are interested in finding is tau, that is the relaxation time. So we'll proceed as we know this equation, that tau is equal to me over nq square into rho. We have the value of me, n, q square and rho. Simply put in the values and we'll get that tau is equal to 2.5 into 10 to the power minus 14 seconds. That is the time between two successive collision, and we have tau. In the second part, it says that assuming that the average speed for free electrons in copper is 1.6 into 10 raised to the power 6 meters per second, and using the result from part A, obviously we will be using the value of tau from part A, calculate the mean free path for electrons in copper. So what we have, value of the average speed for free electrons, then tau from part A. We have to find the mean free path, that is represented by L over here. The solution for this is L is equals to V into tau. So put in the values and we'll get mean free path to be equals to 4.4 into 10 to the power minus 8 meters. So these two parts are very easy to solve if you know the formula. So moving on to the next example, that is 27.6. This is related to resistivity and resistance, which are affected by change in temperature. So a resistance thermometer, which measures temperature by measuring the change in resistance of conductor, is made from platinum and has a resistance of 50 ohms at 20 degrees Celsius. When immersed in a vessel containing melting indium, its resistance increases to 76.8 ohms. Calculate the melting point of indium. So the data given in this question is R naught, that is the initial resistance 50 ohm, R 76.8 ohms. Initial temperature is 20 degrees Celsius, and alpha, that is the coefficient of resistivity, is 3.92 into 10 to the power minus 3 per degree Celsius. Now the solution for this problem is we will use the formula R is equal to R naught into 1 plus alpha delta T. We have the value of R naught, and alpha. So putting in the values, 76.8 divided by 50 equals to 1 plus alpha delta T. I get 1.56 equals to 1 plus alpha delta T. Subtracting 1 on the right hand side from the value on the left hand side, this will give 0.536 equals to alpha delta T. We have the value of alpha, so I'll divide the value on the left hand side with the value of alpha. I get delta t. I know that delta t is equal to t minus t naught, where the value of t naught is 20 degrees Celsius. So t minus 20 equals to 136.73. I'll add this minus 20 on this right hand side, so I'll get t equals to 156.73, which is approximately 157 degrees Celsius. So this is a simple problem again. So if you know the initial and the final resistance and temperature accurately, that this temperature is initial and the other one is final temperature, you can easily calculate the problem related to resistance or resistivity varying with temperature.